This is a video where I'm going to talk about something that is outside of the normal scope of the lectures, but will include parts that are covered in the lecture. So I'm going to talk a bit about damp-free vibration, just to give you some ideas about things, but also to introduce and give you an introduction to damp force vibrations. And in particular to highlight the differences with damp-free vibrations as a goal here. When dealing with damp-free vibration, we often have talked about different ways of dealing with this, but the approach taken in this course, and that's not, it's something to get used to, is that it's a cookbook. And we've sort of said, okay, here's a set of equations that you use, but you can see here, for example, that you have an envelope defined by some sort of event where, say, for example, you have let me make that a damper because that looks more like a damper, and a spring attached. The oscillations come from the spring. The dampening or the reduction in amplitude of the displacement, x is the displacement, t is time, is occurring because of the damper. So you have an envelope that defines the motion of this spring mass system, and you need to know where everything is going. So if you look here, we have the typical cookbook equation that we sort of force you to derive in order to solve these problems. And that form is going to be something that looks like m lambda squared plus c lambda plus k equals 0. And then we tell you, look, the standard form of this expression is minus c over 2m plus or minus c over 2m quantity squared minus k over m, which is omega n squared, the natural frequency squared. And then we say, well, you know, your critical damping coefficient is twice mass times omega n. But remember, it's based on this equation where you have to calculate C equivalent, K equivalent, mass equivalent. And often you normalize by everything, so you know what all the terms are. For light damping, you have a case where you have C, the damping coefficient of the system, which is less than the critical damping, and it's really C equivalent. And that has a form x equals minus c over 2mt, c1 sine omega dt plus c2 cos omega dt. And omega d is the damp frequency, and it's calculated by taking the square root of 1 minus c over c squared, damping coefficient, over critical damping coefficient multiplied by the natural frequency. This is square rooted, of course. You had two other cases, critical damping, which essentially goes down directly in towards zero amplitude. It doesn't quite achieve it because it's an exponent, but as it gets smaller and smaller, it approaches closer and closer to zero. You'll notice here that there's no damping coefficient, or there's no vibration of the motion because there's no sine or cosine term. And if you look at heavy damping, it sort of looks like this, and it's slightly different, and you have lambda 1, lambda 2, and those lambdas come from this relationship right here. So all of this is there to sort of solve through for the standard cases. As you go beyond that, we have damp force vibration, and damp force vibration really is the same equation as you used before. This is the free damped with the addition of the forced. So we did cases that are part of the course that are only for free undamped vibration, or free force vibration, excuse me. But it's really not much of a stretch to go to the next step, which is this, where you have some sort of forcing frequency sine omega ft, x equals x complementary, which is sort of the zero case here, where this is sort of eliminated, plus the particular solution for this particular case. Now, if you look at what's happening here, you can say, well, you have xm is over the forcing frequency divided by k, which is kind of the displacement of a spring, xm over delta, and you have something called the magnification factor, 1 minus the frequency that you're driving the system at over omega n. As you can see here, you expect as this approaches 0, this will go towards infinity. And as you see in the figure above, when c over cc starts to approach 0.1 or so, of something that is at an omega frequency which equals omega n, you start to get to a case where you have an infinite amplitude. So this is a case where maybe none of you will understand it as well, but when I was an undergrad, I would drive in a 19 Chevy Nova that would constantly vibrate like crazy at about 100 kilometers an hour, and that was not much of an excuse if the OPP pulled you over. So if you continue, you can also sort of get the phase difference between the forcing and steady response, 2 over C over CC, omega F omega N, 1 minus omega F omega N. So you have all of this information that you can kind of work from, and you get sort of these pictures of the motion. And the important thing is this forcing frequency. That's the only difference that you have here in the case of force damping. So it's not, this is not a big step. It's a small step, and the only thing that you need to remember here is that we often treat this as a cookbook. We tend to say, okay, here's the answer, and you write it in this form, you solve sort of the balance equation, and then you get this. So it's not really a lot more work than that, but it's kind of good to sort of recognize what it is. Let's do two cases, a free damp vibration, and it's a simple case of mass, damper, and spring, and it's displacing in the positive x direction. You have mass of 3 kilograms, damping coefficients 2 Newton seconds per meter, and K, which is 13 newtons per meter. The final form of the equation we want is this, and this is a case which has been solved in various forms, and so we already know what it's going to look like, and we don't I don't do the force balance on this because I already know what it's going to look like. I mean, this is not a complex case. And this is free damp vibration, and the solution takes the form of x equals e to lambda t, and so when I do x double dot, I get m lambda squared e lambda t, x dot, I get lambda e lambda t, and x, I get e lambda t. So I'm going to cancel those out. And when I cancel those out, I end up with an expression that looks like this, m lambda squared plus e lambda plus k equals 0. So now I can solve through and calculate what the terms are. So I get lambda 1, which is equal to minus c over 2m plus square root c over 2m squared minus k over m. And the other one where the only difference is instead of plus, I have a minus. Now you'll note here, I'm not solving this in terms of numerical values because I don't see much value in that, and it helps me in my organization of the problem. Okay, this term is about minus 4.22 if I do the numbers, and the system is underdamped. So the solution then has this form right here, which is a standard form of the solution, x equals e to the minus c over 2m, t a sine omega dt, b cos omega dt. And then I substitute the terms in, put the numbers now, 3x double dot, 2x dot plus 13 equals 0, divide it out, and I have the various terms that I want. So I can have k over m right here. I have c over 2m, c over m essentially, but it's c over and then divide by half, square it. And I'll get the number of 2.05 hertz, and I have this as my final sort of form of the solution for free damp vibration. If I look at the magnification factor and I say, look, it's equal to 5 when omega naught over omega n is equal to 1, and omega naught again is that frequency over here, then I can try and calculate it for a case where it's 10. So the magnification factor is what we just defined on the previous slide, and I just sort of did this z factor right here, which is c over c critical. Substitute all the numbers in. I get 5 is equal to 1 over 2 sigma, or 2c, excuse me, and c, so for the sake of spelling it out, because I always called it squiggly, is this. Is 1 over c is equal to 10, and c is equal to 1 over 10. For a magnification factor of 10, same thing, 1 over c, but now it's equal to 20, and c is going to be 1 over 20. So this just tells you what the difference in the various critical damping coefficients are. Let's go to a more complex case. This is force vibration, and I've again done a case where I've got 14 kilogram rod subjected to a periodic force of 32 sine 6t newtons, t's in seconds. Determine the steady state amplitude max of the rod about point B, which is right here. Assume theta is small. And I've split this up into 3 parts. I've got a length of this rod of 0.9 meters. I've got that, which I've defined already. Damping coefficient of 300 newton second meters, and K of 3.500 newtons per meter, 3.5 kilonewtons per meter. And what I want to do is sort of give it a small twist. And so that's what I've done. I've just sort of twisted it a little bit. I've put the theta, and they don't make much sense yet, but they will in a second. I have the reaction force at the pin, By, Bx. And I also have defined my positive directions. Positive is up and to the right. I put in all of my forces. That's where the theta start to make sense. You know, there, and there. And I have all of my terms now for the expression. So what do? Rod is in equilibrium when theta is equal to 0, and this is going to have 0 velocity, so this will be 0. And this is equal to 0 because I'm not forcing it. So that gives me the force in the spring, and that's equal to mg divided by 2. So the force in the spring is also associated with the displacement, and I can just say that displacement, the initial spring displacement, is going to be mg over 2k. So at 0 degrees, I know the spring is compressed, because otherwise it's not in equilibrium. So some moments about B. Now, the next thing, I'm going to have the rod rotate by theta, and the spring is going to compress by a distance by its arc length, L over 3 theta. So that distance that it additionally compresses is just going to be that. The velocity of point C, which is how I'm going to determine what the damping force is going to be y dot C. So the velocity at C, and remember these are very small displacements. Theta is always small, and I get y dot C again from the arc length, which is L over 3 omega, or theta dot, excuse me. And so I've got that, I've got all those terms, and then I need to calculate my moment of inertia about point B. Point B, I know the moment of inertia of a rod, 1/12 ml squared, L is the total length, and the distance from the point B, or from the center of mass, which is somewhere about here, is going to be that L over 6. So that's where that L over 6 is coming from. So if I do sum of moments about B, I have FA, which is acting over a distance L over 3 times cos theta, so very small distance. I have FC over here, cos theta L over 3, it's going in the same direction. It's causing a counterclockwise rotation, and so it's positive. I have minus F cos theta 2/3 L, which is from here to B. Okay, that's fine. And I have the weight force, which is acting over distance L over 6. On the other side, I have a problem, and I haven't quite figured out how to deal with it yet, but I'm going to figure it out in a few minutes, which is that moment of inertia times theta dot, so IB theta double dot, is going to give me the term on the right-hand side. So if I do that, I put in all the terms. I have spring force, which is just going to be S naught plus the displacement, cos theta L over 3. This is not a really good term, but that y dot C is cy dot C, cos theta L over 3. And then I have 30 sine 6t cos theta 2/3 L, which is the forcing frequency over the distance, mg L over 6 IB theta double dot. So I'm going to get rid of the static equilibrium term, which is what I typically do. And this is the standard approach taken in the textbook. And I did one case where I didn't do that. It's kind of a cool way to do it. And if you want to take a look, there's another video for that. So I end up with k L over 3 theta cos theta L over 3, C L over 3 theta dot. I'm just substituting my y dot C L over 3 minus IB theta double dot. Now this is a problem, but I brought this forcing term to the right hand side, and that's positive, so that's good. But my equation really has to be positive. Like me, a positive person. So I'm going to assume that theta double dot is actually clockwise, which is kind of a reasonable assumption. I kind of expect that based on sort of what I'm looking at there, most of the forces are on the right-hand side of B and one force is on the left-hand side. And so I'm going to assume that that direction, that rotation, is going to be positive or negative. And so I can make that IB theta double dot term as a positive value by saying theta double dot is really negative theta double dot. And so I've substituted it in. This is, I'm making an assumption, but again, remember, part of the problem with this approach or in this chapter is often we do not really solve these problems. We fit them into an equation that matches our recipe and then we solve at that point. But we don't necessarily solve very much here. So it's generally you're trying to set it up, but you have to have a justification. So there, my justification was theta double dot is clockwise, and that allows me to do this. So I end up with this expression. And so all the terms are sort of off a little bit because it should be the other way around, theta double dot, theta, and theta, or theta dot, and then theta, and is equal to 36 sine t cos theta 2/3 L. But I can take all of these terms right here, the cos theta, and just eliminate them because cos theta, you know, is approximately 1. And there you go, I wrote it out too. And so for very small thetas, it's reasonable. And so for theta double dot, if I substitute all the numbers in, I get theta double dot plus 21.43 theta dot, 250 theta, equals 15.24 sine 6t. Now this is just substituting in numbers, and again I've tried to solve this almost to the end as a variable problem, and again I find these much easier because I can visualize what I'm doing, and when I make a mistake it's often easier for me to see. So I have this as my governing equation for the motion. I have C equivalent, so the C equivalent for this system is 300 newton seconds per meter. My K equivalent is 3,500 newtons per meter. So that's the same. That's kind of a little bit different than the original for the other term. And I've got F naught equivalent of 213.3 newtons. So I've got slightly different results. My natural frequency for the system is K over M, and that's 15.8 hertz. My critical value, twice m omega n, is 442.7 newton seconds per meter, and my equivalent over critical is 0.67 or 0.68. And my omega forcing over omega natural is 0.379. So I substitute all of these terms in for my displacement, x sub m. And if I do that, I get F sub n, which is F naught over K, and then these terms I've just substituted in the expression, and I get an XM of a very small distance of about 6 centimeters. So over a distance of 90 centimeters, I've got 6 centimeters up. And I'm still going to assume it's relatively short. And I'm going to say that XM is equal to L over 3 theta max. And so I divide that by L over 3, get 0.2 rads, and I get about 11.7 degrees as my final result. You got to remember to follow the equations. This is not one of the chapters where you do a lot of innovation in terms of how you think about it. You really need to make sure it follows our standard form. And later on in the advanced courses that you'll take, you'll do more and better sort of problems looking at vibrations. And I certainly encourage you as you go forward. Vibrations is actually quite fascinating. Thank you very much, and we'll talk again.